Okay, so we can quickly see what we did so far. So nothing is clear. How many? 0. Everything is clear is 2. So partially clear. Rest is in partial allocation type of situation. So what we did so far is we defined what is fair allocation. Formally we defined for indivisible goods. We defined in general, but then we focused on indivisible goods, right. Then we defined two fairness notions. We defined two fairness notions so far, proportionality and be free. Proportionality, we just said that okay, it does not always exist, it is computationally hard. Then we completely switched to NB free allocation, right. NB free allocation also we said that it does not always exist, computationally also it is hard, right. Then we said okay, then what next we could do. So we moved to EF1 allocation scenario. So we said that okay, fine, you envy me, but let us remove one good, then also do you envy me, okay. That was the notion of EF1, okay. Then for additive valuation we looked at round robin algorithm, and for monotone valuations what algorithm we looked at? Envy cycle elimination algorithm, right. And then we said okay, EF1 is very weak notion of envy freeness, asking too much from people, right, that if you remove even house then also you do not envy. So we defined the notion of envy freeness up to any good, right, just remove any good then also do I envy, okay. So what did we say there? That also does not always exist, but for the general and identical valuations it exists, right, but it was computationally hard, okay. For identical valuations in the EF scenario we said it does not exist, even for additive it may not exist, right, but for EFX we had at least something more than envy free, right, then only it will make sense to study that, right. If it is not giving anything extra, then why to study that, okay. So we looked at EFX and then we talked about efficiency notion. We just talked about Pareto optimality so far.
Chronologically in literature, EFX came later than EF1.
EFX is just 2018.
Because it seems.
And 7 years later, 11 was EF1.
Like people didn't think about EFX.
This much I don't know. I recently started working in this domain, so I don't know why there was a such a long gap and all those things. EF1 definition of EF1 and EFX. Why people took 6-7 years to define.
Sometimes what happens is you do not have a real life applications where you see this phenomenon. So many of this theory is driven by what you see in economical market and this and that. So to justify your definition, right? So it is other way, like in mathematics we define and then we do something. Here it is like what you see you try to model. So it could also be because just they didn't notice or they didn't see something like that being appearing in the
Right, okay. So EF1 and PO we saw that it exists, right, because every M&W question is optimization question. There is nothing about existence there, right. There are allocation, for every allocation I can find Nash welfare, out of that I want to output the one that maximizes my Nash welfare, right. So there is no point about no question of existence there, okay. So it exists, and then we said that okay, whatever maximizes Nash welfare is my EF1 and PO for additive valuations, okay. Okay, this was question for you which Sanjay will discuss next, okay. I mean you will actually tell him and he will verify, okay. So now let's talk about EFX and Pareto optimal solution. Okay. Every M&W solution allocation is EFX and PO for additive valuation and two value instances. Now what is the meaning of two value instances? That every agent is just giving two values, like there are just two values A and B, let's say, right? Now I will give to every item, I will give value either A or B. Okay. And it can also be computed in polynomial time. See, there is a difference here also. This existential result is 20 and computation result is 21. Okay. For additive valuation and 3 value instances, I'm sorry, this is also GUG. I will fix it in the slides. Yeah, it is the same paper. It need not exist. Okay. And the checking the existence of EFS and PO for additive valuation and 3 value instances is NP-hard. Okay.
What is 2 value and 3 value instances?
You are sleeping, I see.
Is it the...
So 2 value instances meaning every agent can give only 2 values to items. That's, let's say there are 2 values A and B. Now to every item I will either give the value A or B. That's it.
Is it equal valuation, like all agents will give same value?
Yeah. Okay. Now for binary valuations, yeah.
All agents give the same value which should be either A or B.
In general, yes, that's the definition of 2 value instances. But as far as I remember, for that it's the A and B. Fix A and B.
But so these are for objects, right? So the
Yes.
subsets of those, like I'm saying. In
So
terms
we
of
are in
like
additive
UI.
valuation setting. No, the result was for additive valuation, right?
It
So
will
you
be
can
equal.
give valuations to every item. Okay. Okay. So EFX and Pareto optimal for binary valuations, we can compute in polynomial time. Okay. Yeah, but this is even simple, right? It's just 0, 1. You're right. Okay. And okay, now let's just see this one. Okay. Okay. Let us say A is any allocation. You start with any allocation. Okay. So here, let's see how much detail we can give, but let's see. I hope it will be at least clear. Okay. So you start with any allocation. It's a complete allocation, but you start with any allocation. Okay. We can assume couple of things about this allocation. I'm not talking about optimality. It's just an allocation. Okay. One thing I said that we can assume that every good is valued positively by at least one agent, right? So I can assume that I will only give a good to an agent who positively value it, right? Right? This is a fair assumption. I mean, it's not an assumption. Without loss of generality, I can say that every maximum allocation will do this, right? Okay. Now let us create a directed graph as follows. Vertex set of GA is same as the set of agents. Okay. Now this is a directed graph, but you will have multiple arcs between the pair of agents. Okay. So for two vertices U and V, okay, this notation, okay, I have written, fine. Add AU intersection PV many arcs from U to V, where PV is the set of items positively valued by V. What does it mean? Okay. So you have currently an allocation A, right? Now there are some items, goods that are positively valued by V also. You will allocate those many arcs. You will add those many arcs between U and V.
So like you mean that some of them could be 0 or negative, or it's just
0. Negative cannot be. So it's a binary valuation thing, meaning every for every good I have value either 0 or 1. Okay. So for two, this is the construction of the graph. Okay. Now how we reallocate here? Let us look at a path from U to V.
so this
where V is positively values and whatever U has intersection with that, those many arcs you make between U and V.
Right. So AU is the bundle assigned to agent U under A, right? So out in that particular allocation, how many goods are positively valued by V? See, the intuition is that those many what you call goods you can move from U to V basically to improve the valuation of V. Will not do that in one go, but that is basically the intuition. Okay, you can imagine that every arc represent a good. Okay, we don't need to label it with good because everything has value 1, right? So in some sense these are identical, so I basically don't need to, okay, but that is basically the meaning. Okay, okay. So let us look at a path from U to V. Okay, let us see what does it denote. This arc denote that there is a good with U that is positively valued by its next vertex in the path, and so on and so forth, right? Okay. Now if I start reallocating one good, I am not talking about same good, all I am saying is take a good from you, give it to the next person, from that person take a good, give it to the next person, and so on and so forth. Okay. What will happen? U, valuation of U will decrease, right? What will happen with the valuation of its next person? Will it change? It will remain same, right? When a good move from U to this next person, its valuation increase because it get one more item, right? But now it give away one item, so utility remains same,
But
right?
the item which you give, that one won't go, that can also go.
It can also, it does not matter. And here we are using the fact that the item that we received is also positively valued, the item that we give away is also positively valued by V, right? Because we assume that you will only give like you will not give an item to an agent if he does not value it positively. Okay, okay. This plus minus keeps happening. Do you observe something here? Whose valuation will change? Only the endpoints, right? So if I know that reallocation needs to happen between U and V, then the choice of path does not matter here, right? Because whoever for the internal vertices, valuation does not change, it remains the same. Okay. So now this is the algorithm. What they do, you start with any allocation with the feasibility criteria that I said. Now you construct this graph, right? For every pair of agents, you find a path, do reallocation, right? And look at the pair that maximizes your Nash welfare after reallocation. Take that one, take that path and start the process again. Okay. Now you see, for the polynomial time algorithm, it was crucial that the choice of path does not matter, right? Any path between U and V, can I find it in polynomial time? I can find it, okay. Who is saying no? Okay. Okay, so this is the algorithm. Okay, now for the correctness part, yeah.
Do we reallocate any object that is in that set, or do we choose,
You reallocate anyone, because again, so here this is the thing, that because every item is positively valued, like equally valued, not just positively, equally valued, right? So I take our item, give away, right? Because of that item, utility increased by 1, give away any item, utility will come drop to the same value. Okay, 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 okay. I have one more slide, after that I will use board. So we will read it later, but this is the one thing which is crucial lemma here, that if I have any suboptimal solution, right, which does not maximizes Nash welfare, then there exist pair of agents u and v such that v is reachable from u in GA, graph you construct with respect to the allocation A, and reallocating the way I said, right, that will give you this much guarantee. Okay. Now, what is A star? A star is optimal solution.
We will start with some EFX allocation or any allocation
Any allocation.
in the previous one.
Huh.
And in this you have written given a suboptimal solution A. From that
Say it again.
like
Okay.
from that
So, remember one result. We said something about EFX, PO, Nash, two values, additive.
Let it always exists.
We said that every MNW solution is EFX and PO for additive valuation and two value instances, right. So, what we are trying to do basically here is finding an allocation that maximizes Nash welfare. But I am only not giving you for two value instances, I am giving you for binary valuation only, right. And if I give you now, if I find an allocation that is that maximizes Nash welfare, then that will be EFX and PO as well, correct. But that, yeah, that's a good point to recall.
What's the difference between A prime and A?
Yeah, I will just say. So, oh, it's not there. Okay, fine. So, A star is Nash optimal solution. A prime is the allocation that we get after reallocating along this path. Okay, and that's all. These are bad notations because I use curly A here and the normal A here, but that's also curly A. Okay. Any questions here? Don't read it. Just read this box thing.
What was that N?
Number of items. Yeah. All it is telling you that, I told you, right, that you find a path, right, that maximizes your Nash welfare and you reallocate on that, right. So, what is this lemma telling you? That if it was suboptimal solution, then there is a guarantee that there exists a pair of agents, right. If you look at a path between them and then you reallocate, there is some guarantee about the improvement of Nash welfare. Okay. Now, what this is telling you, that if I keep doing it, if it is a suboptimal solution, I will find pair of agents because of my lemma, right. I will reallocate, but after these many iterations, I will reach to the optima. Okay. Is that okay? Okay. And this is this part I will not prove because this is just applying, just solving math, and that's a simple math only, just calculation, that in every iteration I have this, then second iteration I will again have this improvement, so and so forth, right, and then it will follow. Okay. And we just need to use the fact that the valuations are integral, that's all. Okay, then it will follow. Okay. Now, let me try to give some intuition for this proof. Okay. So, this A star is your optimal solution. Right, and A is your current. When I am saying solution, I mean allocation. Okay, current solution. Okay. Now, let us understand what is happening with respect to A star and A. Okay. what are the items that are currently allocated to an agent in A and in to A star in this thing. Okay. So, again let us draw a graph, but this graph is for analysis purpose only. Okay. So, with respect to A, we construct a graph G star A. Okay. Now, what is G star A? Again the vertex set is same as the set of agents. Okay. So, I have some set of agents. Look at U and V. Okay. I draw again arcs, but how many? Now, I can see what is A star, right. Look at the items which are currently allocated to U in A and to A star or to V in A star. Okay. So, let us say G is a good which belongs to AU intersection A star V. Okay. Then corresponding to this G, we have an arc from U to V. Is the construction of G star A clear? This is only for analysis purpose. Clearly, I cannot draw it in my algorithm. My algorithm is over. I cannot see A star, so I cannot create this graph. This is just for understand and analysis purpose. Okay. So, the construction of G star is clear, right? Okay. Now, the claim is that this graph G can be partitioned into paths and cycles. Okay. It is not immediate, I will just tell you why. The graph can be partitioned into edge disjoint paths, that is also important here.
So, we have edges from V to U.
You may have. Okay. So, this is the one thing we will show that this happens. Secondly, we can argue that in my collection there is a path, not every path, but there is a path on which if you reallocate, you will have this guarantee. And third thing is, such a path is there in my G prime A, the graph that I constructed. Okay. No, A prime is the allocation I obtain after reallocating, okay. But I create a graph with respect to my current allocation. Okay. Okay. So, let us construct another graph. So, this was my G star. Okay. What is G star? V of G star A. Let us erase the picture. So, do you want picture or do you want in words? Picture. Okay. So, construction of G star is clear, right? Okay. Let us construct a H star. Okay. What is H star? For every vertex U, look at its in degree and out degree. Whatever is maximum, create those many copies of U. Okay. So, let us say with respect to U, I create U1, U2, U3, something. Okay. How many copies? Max of in degree of U, out degree of U. I will say Y in a minute. Okay. Correct, in G star. In G star, yeah, A. Okay. Okay. Now, look at in edge arcs coming to U. Okay. Map them to, let us say there are L many arcs. L in neighbors of U. Okay. Let us map coming into U, yes, but there are L many arcs coming to U. It means that in degree of U is some L. Okay. Let us map them to U1 to UL. Okay. Map, let us call it in edges of U to U1 to UL. Okay. Let us say L prime is out, let us call it in degree. L prime is out degree of U. Okay. So, map out edges to U1 UL prime. Okay. So, how does it look? It looks like this. Let me trace at least this part. So, whatever was maximum, you created those many copies, right. So, you have U1, you have U2. Are you able to see this part? Right. So, you have this, right. Now, what will I do? In degree, I start mapping, right. Then out degree, this is important, out degree also you start mapping from U1. Out degree might be large, you go like this. Okay. Okay. Now, how did I, so this was mapping. Okay. I mapped this arc to this out arc to this. I map this out arc to this to this, right. Now, how do I add edges in H star? If there, let us say there was an arc between U and V, right, and I mapped this arc to UI and Vj. Okay. So, I will have arc between UI to Vj, whatever, in H star. Is the construction of H star clear? Simple. Look at in degree and out degree of vertices in G star. Whatever is maximum, create those many copies of a vertex. This is the vertex set. Okay. Now, to every arc coming to this, map them to U1 to whatever is in degree. 1 to 1 mapping is important here. Okay. Similarly, out degrees, out edges, you map. Okay. Now, look at an arc between U and V. Okay. You must have mapped U to V, right. So, you must have mapped this arc to one of the copy of U, and you must have mapped this arc to one of the copy of V. Correct? Correct? Okay. So, just add arc between those copies in H star. That is it. What can we say about the in degree and out degrees of vertices in H star? At most one, correct? Do you all agree? So, at least can I say that H star is a collection of paths and cycles? Correct? Is this fine with everyone? Okay. One more thing I need to define actually. Let us partition the vertex set into two sets, excess and deficient. Okay. What does excess mean and deficient? Excess means that this particular agent has more items in A as compared to an A star. This has excess of goods, right, and deficient means it is deficient of goods. Okay. So, excess, here we will have agents V belongs to N such that size also I can talk. because valuation is 1 only, right. So, I can write in terms of that also. A I is greater than AJ. Okay. These are excess agents. Deficient agents are
Shouldn't that be A star I?
you are right.
Should be A star I.
It's not I J, it's I, you are right.
Star should be on the first.
So, this is how I am defining excess, meaning currently you have excess of goods, and deficient meaning currently you are deficient of goods. Okay? Okay. Now, one thing to note here is that if you look at a path, right, the source vertex is what? Excess or deficient? Right, excess. This is fine with everybody, right? The source vertex is excess, right? Because why is it source? Nobody is coming into it, so it's excess. What about sink vertex? It is deficient. Okay. So, at least now I know that when I am doing reallocation, right, I am giving away from the excess vertex and giving something to deficient vertex, right. This part is okay, right. Okay. Okay. So, this is fine. Now, if we go back to H star, I know that this is collection of paths and cycles. Okay. And all these are disjoint. Let us take it back to your G star. Do you see that path here correspond to path there? G star. Path in H star. So, H star we are not doing anything, we are just to analyze, we created H star, right. Now, in H star it is easy to visualize paths, right. This is how it looks like, because H star itself is a collection of paths and cycles, correct, right. Now, what we are saying, let us take it back to G star. What is the meaning of taking back to G star? Look at a path, right. In this path you have copies of U and V, right. When you are taking it back to G star, meaning take U and V. Okay. Clearly it is going to be a path, right, or cycles there, correct. All the arcs which are in G star, do you agree all the arcs are in H star? H star is path, collection of paths and cycles. I am taking it back, then also path correspond to path, cycle correspond to cycle. So, do we agree that G star has collection of paths and cycle? One thing which I did not argue is that these are disjoint in G star, I will say that, but so far do you agree that these are paths and cycles in G star? Yes, okay. Now, why they are? Okay, before even going to that, are cycle useful for me for reallocation? No, right. So, forget about cycles, I do not care about cycles. Let us just focus on paths now. Okay. So, I have paths P1 to Pk. We have time till 3:30, right? Okay. So, let us say this is the path in your G star, the collection of paths in G star. Why this is edge disjoint? Notice there every path, every edge is corresponding to a good, correct, and corresponding to a good I have only one arc, right, and here also you have you know those many arcs that you could move, correct, right. So, the number of arcs you have there, the number of arcs you have even here in G star, correct. Exactly, they are same, right. So, this is edge disjoint, right, because arcs there are corresponding to goods in both G star as well as A star, right, and there is only one arc corresponding. Can we have two arcs corresponding to a good? What is the meaning of adding an arc? This good currently belongs to A, but finally it belongs to A star. So, I can have only one arc corresponding to a good, correct, right. So, we have only one arc corresponding to a good, right. So, this gives you that is also edge disjoint. Okay. Okay. I need to move to a different topic. So, I will just leave this part that there again this is just then mess that there exists one path in this collection, right, that gives you this thing. You need to apply telescopic series summation and concavity of logarithm log here to say that. Okay. But we can argue that there exists one path here which does that job, right. Now, why does that path exist in my graph? Because if you notice G star A, it can only be subgraph of my graph, right. What I did in my graph in G prime, currently this is with you and this is positively valued by V. In A star, if you in G star if you look at it, right, when you have this arc, right, this is AU intersection A star V, right, then clearly it belongs to AU intersection PV, correct, PV meaning positively valued items, right. So, if you have arc here, you have arc in your original graph as well, right, that is why this path exists in your graph as well. Is this okay? Somewhat, of course, it is only a sketch, we have not argued everything completely. Okay. So, the idea of the proof is as follows. Okay. There are some fillers I am not asking to do in tutorial because you do not have time to work it out, okay. But you can go back and check this paper if you are interested. Okay. So, the point is here that we constructed G star to understand what is the difference between A and A star, correct. That is the purpose of constructing graph G star, right. Then we said, okay, then G star can be decomposed into paths and cycles, can be partitioned, whatever you want to call. Cycles are not a useful object for me, forget it. Paths are the only useful objects for me, right. Okay, then fine, there is a path that achieves this thing, okay, and such a path exists in my graph as well, right, and I am anyway reallocating on the one which maximizes my Nash, okay. So, I will achieve this, okay. Okay. So, that is all I want to say from the classical literature of fair allocation. We will move to something else now, that is really then invitation, because it is only half an hour. Oh, okay. So, this came at the wrong timing. So, okay, this is IIT Jodhpur campus, which is green, not desert. Okay. So, purpose is not to show you campus here, purpose is to tell you something else. So, this school we organize every year at IIT Jodhpur. Okay. So, this year the school is winter school on AI and TCS. One of the track is Costco. Okay. So, this will be third school in the series. The school is from 11 to 13. Winter school on AI and TCS, the full event is from 9 to 13. 9 and 10 is the AI part, okay, and the focus of AI part is generative AI. Do not ask me what it is, I do not know, but generative AI it is something, okay. So, the focus of this school, why am I telling you this thing? The reason is the focus is fair and efficiency in allocation problem, okay. So, of course, we in 3 hours I think we could not look at many of the things, but in these 3 days we will go deeper into these topics, okay. Okay, so this is the confirmed list of speakers. We may have some more Okay. Yes, this is this Sanjay only. Okay. So, this is we may have some more, some have not confirmed yet. Okay. So, let us move to another topic now. Okay. So, participatory budgeting. Now, because you understand what is voting theory and what is fair division. So, this is the right time to talk about participatory budgeting. Okay. So, how many of you have heard about participatory budgeting? You have heard? Okay. In what context?
I read the below line and then panchayat division.
Right. Okay. So, democratic process in which community members decide how to spend public money. Okay. So, what do we mean by this? So, let us say you have some projects to be for a city. Okay. Of course, you do not have infinite money, right, so that you can fund everything. If it is, then we have no problem, right, and every project will incur some cost. Okay. So, we want to find a subset of items, a subset of projects, right, that could be funded within our budget. It is a simple problem, right, but we do not like simple problems. So, what we want to involve voters. Okay. So, you are citizen, right, and these projects are for you only, right. So, why just somebody else can decide? That is not fair. Okay. So, you are asked to either approve projects of your choice or rank projects of your choice. You may give rank everyone, right, these are different models, or you may rank only the partial, subset of projects, right, or you may also give the cardinal utilities that we are talking since morning, right. Okay. Okay. So, all these terms you understand, right, now? If not, then just say it is okay. Approval you understand, right?
There was someone would give you some ranking and someone would give you some set and you say yes or no.
No, nobody is giving me ranking. So, this is a subset of projects I know, right, that are in the market. I will just say whether I like this project or not like this project, that is it, that is approval. Okay. You might have seen this in voting lectures at least, right, huh? Correct, correct. Okay. And there is one more model here which I forgot to mention, but that is called cumulative voting, which Sakit was saying in the morning, that you have utility and that is what you want to split, right. But here instead of utility, government give you that this is the money and how would you like to spend it over the projects. Okay. That is called cumulative voting. So, for this part we will not go anywhere into the algorithms, I am just introducing you this field. Okay. Okay. And now goal is to choose some projects that maximizes the voter satisfaction and the total cost is within our budget. Okay. Okay. So, this is not completely artificial problem. Okay. This has been used. So, this is from the 2024 participatory budgeting results of Cambridge. Okay. So, the whole PB process is actually this, okay, but we mainly focus on this third part, okay, participatory budgeting community that is doing this computational research, that focus on this part, okay. Proposal development, idea collection, this all we do not care, there we do not have computational questions, okay. 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 So, this QR code, if you do not believe me and if you want to scan and verify on your own, so this is the QR code for that. Okay. Okay. So, it started in, you can read, is it readable? It started actually in Brazil, see, in 1990, okay, maybe it is written 1990 here, so I think it is early, but fine. This is some article again, right. and now it has been, this is just a list, because on one slide I could only fit this much, right. But you can see that these more than 40, okay, maybe even the count is more. But my interest is not anything else, but recently only, maybe few months ago only, I saw that it was actually used in India as well. Earlier I thought that no, it is not India, it is only US and Europe. Okay. So, it started from Kerala. Why are we interested in participatory budgeting? Okay, I forgot, when I took screenshots I did not add the reference, and now I could not find it. But the main point here is again the same thing, that these projects are for you, right. So, your opinion should matter, right. And again, why are you interested in going and voting? For the same reason, right. So, that is the thing. So, this is the graph for Pune election. Okay. In Pune it started in 2006, and then this is the graph. You can see that with the time, it is the money spent for the participatory budgeting is only increasing. Okay. It was tried in Bangalore as well, there was proposal for Delhi also, but maybe I think they did not get the approval or something. So, whatever resources I found, I only know 3 cities, Kerala, Bangalore and Pune. Okay. Okay. Other applications of PB. So, if you work in these domains, then you can maybe understand on your own what are these applications. I do not know much about blockchain and all, but there are applications, and actually PB community is also working into looking at these things from the blockchain perspective as well, right. So, as in Google auctions and all those things, ranking and all those things, we know that money is involved. So, that is why PB applications come there as well. Locating public facilities, of course, that we know that PB has applications, and this I really do not know how to improve the quality of genetic algorithms using PB, but it has application. Okay.
The second one, how is it related to PB?
So, I think that this is only my guess. Why? So, it is maybe because you know, some pages are more liked by people, ranking when we come up with the Google ranking. So, some pages are liked more by this thing, and I do not know if the payment is involved there, or maybe with respect to ads also it is there. No, it is talking about web pages.
So, what would people do in this? Go and vote for the page?
I think it is not like they are directly voting, but it is based on the available data. Google is, let us say, learning that what is which web page is liked by more people. Accordingly, they are changing the rankings. Okay. Okay. So, again, this is the model. If we forget about the history and all these things. So, this is the model that you have projects, you have cost of all the projects, you have budget, approval model, ranking model, so on and so forth. Okay. Okay. The most we will focus on approval ranking, approval voting. Okay. Okay. So, this is something which needs to be observed here, that voting participatory budgeting is something at the intersection of voting theory and fair division. Can you say why? What are we dividing here? Exactly, money.
And the ordering is not cardinal, it's ordinal.
It could be anything in voting theory, right? Indeed, I said we will focus for the rest of the talk on approval voting, but it could be approval, ranking, cardinal, anything, right? But in fair division, yes, we largely look at cardinal model, but who stops? If the things make sense, right? But of course, NB free and all those things will stop making sense when we have approval thing, right? But fairness is some sort of fairness is still there, right? When we are, so here it is not immediate, that is why we are saying that it is something at the intersection, right? It is not completely fair division problem, right? Money is involved, third party is involved who is not getting items, they are not getting the projects. Projects are also shared, correct? So, that is the thing. Now, so let us say you have some money, why are we saying it meets fair division? So, this is the money, right, and you would like to divide this money among several projects, right. Earlier what was happening? Person who is getting something, they had valuations, but now they do not have valuations. Okay. Citizens' opinion matter here. Okay. So, this is how I call it. Participatory budgeting is fair division of money considering third party, meaning voters' opinion. Okay. So, in my opinion, that is the gap, that voting theory, participatory budgeting problem has largely looked by the voting theory community, not the fair division community. Okay. Okay. But it makes sense to think about fairness notions that could be used for your participatory budgeting, or that makes sense there.
So in this, say I have more approvals for something, so that implies that I will give it more budget?
I will come to the definitions, okay, how we derive the utility. Okay. So, let us think about some PB rules now. The rule that is largely used by these countries who are using participatory budgeting is greedy rule. Okay. So, what we do, they have again approval ballot only, and then they order the projects in the decreasing order of their approval scores. Okay. Approval score is the, for a project, let us look at the number of voters who are approving this project. Okay. That is the approval score. Okay. And then you go over the list and fund the project if the budget limit suffices. Okay. So, for example, this is again the example from the 2024 Cambridge election. So, what they had, this is the budget they used, right, and funded first 8 projects, right, but let us say I change it to this. Okay, $20 lakh. Okay. Okay. So, then after 7th project, I do not have fund for the 8th project, right. I mean, I have not written the values what sum up to, but you believe me that after this I do not have leftover budget to fund this much. Okay. These are the approval scores and these are the costs. Okay. So, what I will do, I will go to the next project and check if it can be funded, it can be funded, and this is like 10th again could not be funded because we do not have budget, and so on and so forth. Okay. This is the rule which is used in Cambridge, I think Canada, Poland, this is the rule. I do not know which one is used in India, that was not mentioned there. Okay. So, do you see any shortcomings of this greedy method? Recall that, huh? Voters are, no, I sorted based on the approval score, right?
But we are like, some projects are choosing such that their votes are less than
Correct.
some projects which are more votes.
Correct, right. So, it may happen, you are right. So, that is a shortcoming of this greedy method, that it may happen that let us say there are a large fraction of voters who approve a single project, right. So, and the cost of that project is very large. Okay. So, now I will fund that project. Now, I do not have fund to I do not have budget to fund any project, right. So, all those remaining voters are like, they are unsatisfied, nothing is funded of their choice, right. So, that is a shortcoming of greedy method. Okay. So, let us talk about some rules based on satisfaction function. Some of these rules I am sure you saw in voting theory lecture. So, satisfaction function, this is a function from this. So, usually we talk about natural numbers because you know satisfaction, why is it rational or something, but of course, one can talk about that. Okay. So, what does it mean? Okay. So, first is to capture the approval vector of a approval set of a voter, and second is to capture the set of projects that will be funded. Okay. Okay. So, this was our input. I will just say it again when I say it more precisely. So, this is the, let us say this is our input. Okay. So, we have some set of projects, some cost for every project, we have some budget, and this is a approval set. So, V1 approves, what is this? School and park, V2 approves another park and bus stop, V3 approves both the parks. Okay. So, this is our approval score. Now, what are the possible satisfaction functions? Okay. So, one possible so this is what I was telling. Okay. So, AV is the approval set of voter V, okay, and S is the subset of projects. Basically, we are trying to see that, let us say I fund the projects in S, then what is the utility or what will be the satisfaction of voter V? Okay. S, fund the projects in S, S is a subset of P. Let us say I fund the projects in S, then what will be the satisfaction of voter V? So, did you see this voting rule in voting theory lectures? Yes? Okay, you are right, that is okay, it is written there, right. So, this is one of the rule to derive the satisfaction, right, that number of projects of my choice that are funded. Okay. Any other suggestions from your side?
Right now we have a approval set, but we could also say that is my most preferred.
So, currently we are in the approval setting. Okay. We are right. When we go to ranking, our satisfaction functions will change accordingly.
We listen to all the people, at least once. We listen to all the people at least once, like include all the people.
Okay. So, you mean that if you fund something, right, from my approval set, I derive the utility 1, otherwise 0, right, 0, 1, I will, yes, that is also one, this is what you are saying or something else? Yeah, okay. You want to listen to everybody at least once, right? Okay. So, I will come to that, that was my fourth satisfaction function actually. So, another is this thing that your utility is related to the cost of the projects. Okay. So, utility and satisfaction actually I am using interchangeably, but yes, satisfaction is what the cost of the projects of your choice that are funded. Okay. This is what you are saying, that if something of your choice is funded, then it is 1, otherwise 0. Okay. This is another one, that look at the set of items, set of projects of your choice that are funded, right, but it is not like that, like this you are getting the from everything, right. So, what is happening here, let us say 2 items of your choice are funded, right. Then for one item you are getting 1, from another item you are getting half. So, it is 1 plus half, right. If you fund 3, it is 1 plus half plus 1 by 3, right. And similarly, you can define several notions.
Why
I'm not saying anything better.
What's the point of this harmonic sum?
This harmonic sum. So this is to say that, you know, in some sense that it is not like, you know, how should I say it? It's not just getting that from every bundle you are getting the exact satisfaction, right? You are just basically it's marginally decreasing, right? So what will happen because of this, right? So for example, earlier, if I okay, just a second. If I look at this satisfaction function, this is just telling you satisfaction function, satisfaction value of one voter, right? Now what is the satisfaction from this outcome? S. Now you can apply again those 2-3 functions, right? What I can do, I can take the addition of satisfaction of all the voters. I can look at, and that is what I can try to maximize. Or I can look at the minimum satisfaction of a voter, that is what I can try to maximize. I can look at the geometric mean of voter satisfaction, and that is what I can try to maximize, right. So all those possible aggregation function you can study, okay. Now coming to your question, let us look at the addition, that is what. Now do you see the difference? If I fund, let us say we two are voters, okay, both the items for me 2 items of my choice are funded, right, and nothing of your choice, right. It has same satisfaction with 1 item of my choice is funded and 1 item of your choice is funded, right. Both has value 2, right. But what will harmonic do? It will give preference to the in this case, suppose I approve some item, you approve some item, okay. No, approval set could be large, but look at the set of projects that are funded, okay. From that, let us say 1 item of your choice is funded and 1 item of my choice is funding. What is our utility? What is the total satisfaction? 2. Take the summation of the voters, right, 2, okay. Let us look at another set of projects, subset of projects. 2 items of my choice is funded, nothing is of your choice is funded, 2, right, okay. But is not at all taking care of the fact that you also needs to be satisfied at least to some extent, right. But what will harmonic do? Harmonic is just an example to capture that, okay. In the first example, when we both were getting, then it is 2. When only I am getting, it is 3/2. So it is trying that, you know, everybody trying, so actually it is trying to basically capture this thing.
It's realizing someone who has more number of items.
Correct. So it's not linear, it's not increasing linearly, right. Satisfaction of a voter is not increasing linearly, okay, and that's the difference, okay. Okay. Yes. So we could consider all these things, right. This is the question. Let's go back to the previous slide now. You know answer. You know the answer. If you are awake and you have done any algorithms course,
We cannot write because you have to check concepts.
but that's a brute force algorithm. That's even for you start doing for shortest path.
No, I'm saying that in polytime you cannot do that if you have to check concepts.
But why do you need to check? You need to think, say some better algorithm, right? Just look, you see. Okay, let me give you a hint. There are some satisfaction functions that you can reduce to the problem you know. Now it depends how many problems you know.
Yes. Third one is the
Give some time, please. It's very.
Binary.
Huh?
You have to
The
maximize
binary
the
location.
intersection. For
Hint, knapsack.
yeah, diffraction. Please try.
Okay, so just think about it. So knapsack of course is a NP hard problem, right? But there is a pseudo polynomial time algorithm for knapsack. Okay, not for all, but at least there are some satisfaction functions for which you can use that pseudo polynomial time algorithm to get a polynomial time algorithm here for knapsack. How many?
Here also we need pseudo-polynomial.
No, here for some of the cases I mean polynomial, for some of the cases I mean pseudo polynomial, and for some of the cases I don't mean anything.
For third, can I do polynomial? Like I have to maximize the intersection.
For third it is actually okay, for third, okay, actually for these, now I have given almost the answer. Third and fourth it is not knapsack. First and two you can think. For one of them it will give you polynomial time algorithm, for one of them it will give pseudo polynomial time algorithm.
Yeah, knapsack is the second.
No.
Huh?
The second one is
It's knapsack.
First one is also knapsack. Think about it. What is knapsack? So knapsack problem is that you have set of items, okay, and for every item you have a profit value and a cost value, okay, and now you want to pick a subset of items whose cost is within the budget and profit is maximized.
This one is special case of second of the series one.
No, why? Because budget constraint is still there.
That is it.
Okay, think about it. It's not difficult. Okay, okay. Actually, you can think. You can think about the reduction. But what gives you polynomial? What gives you pseudo polynomial? That we can say only once you know the knapsack DP.
I mean, budget is the total bag size, like the size of bag, and prices are such like the weights, and values are the satisfaction for.
Think about it. Okay. We have 2 more days, right? And one day we have tutorial. Anyway, you don't stay for the tutorial. Okay. Okay. So let's. I'm very tired, so I'll just sit here and say. So some of the fairness criteria that we looked at here are. I hope I'm audible. You don't need to see me. Okay. So maximize the voters' satisfaction is what we are dealing as of now, right? Now here we ignored the interaction between the projects, right? What do we mean by this? So let's say we had these 3 projects, okay? What are these 3 projects? 2 projects are building schools in the area, some area which are geographically close to each other, and third project is to build a road from this green region to whatever is that region, I can't see the colors, okay, that P1 region, right? So if let's look at this voter who likes P1 and P2 and he's just living in the middle of this thing, right? He's actually, it's fine that even if one of them is a school is there, right? And let's say there are a lot of voters of type this thing, right? And now if I apply at least greedy approval method, if I apply, right, based on the score, if I start funding, then it may happen that I end up funding P1 and P2 and not P3, right? So what will happen that there was a lot of students actually now who will not be able to go to this thing, right? So it was better to fund, because P1 and P2 funding both is of no use. So maybe it was better to fund P1 and P3. Okay. So this is the effect of project substitution. Okay. Similarly, we could have the effect of project complementarity. What does that mean? Let us say there are, again the same example, but let us say there is a voter there are a lot of voters, there is a voter of type P1 and P3. Okay. But the many voters are like P1, P3, so it's fine. but the cost of P3 is so high that both P1 and, okay, of course we can assume that cost of every project is within the budget, okay, but cost of P3 is so high that both cannot be funded, right? Now if you fund just P1, it's of no use again, right? If you just build a road, maybe road is not going anywhere else, again of no use, right? So so there is a interaction structure between the project that needs to be taken care of. Okay, so this is the formal model now, that to capture the interaction structure you have a function. Okay, and now goal is to find a bundle within budget B that respects voters' preferences and also take care of the interaction structure. Okay. Okay. Maybe this is not of much interest to you, that it is just the interaction structure function that will tell you that, okay, if you fund this together, then what will be the my utility. Okay, so I'll just skip it because I don't think, I just want to tell you that there are such things which we considered. Second fairness criteria is that, let's say you want to organize a birthday party. Okay, so of course you need to allocate again your money to various things involved in the birthday party, right? Okay, I actually changed example, that is why it's so weird. Travel, you don't need money for travel. Okay, or maybe your venue is so far, that's why you need travel money. But you need to spend some money on the venue, you need to spend some money for decoration, food, return gifts, and maybe something else. Okay, so this division also you need to take care. Okay, so what you can do that, okay, this is the part for which I want to fund the project, and this is the budget for each group, right? Okay, so like this we have now grouped the projects of same type, right? And now within the budget you will fund the project from that particular group. Okay, so goal is to find a bundle that maximizes voter satisfaction again within global budget limit, whatever we had earlier, respecting the group wise budget. Okay, of course all these problems are NP hard, then we talked about, forget it. It's just a mathematical definition of whatever I said. Okay, okay, that's all. Thank you. If you have any questions, you can ask.
I have a question regarding so there would be a question of strategic proofness in this as well, right?
Yes, one can ask, but there's not much. I don't think there's much from this in this PB world.
Like what impossibility theorems could also be formulated in this case.
Right. So whatever impossibility theorems you have for, okay, if you can actually see here that participatory budgeting is a generalization of multi-winner voting, right? There you do not have cost, here you have cost, right? So whatever theorems, impossibility theorems you have there, you have here as well. Whatever that can be manipulated even here. Okay. There is also one thing, I mean, I don't think I need to say too much here, but there is also a model of delegations in voting theory, where you do not, you are lazy, right? You don't want to vote, okay? You delegate your vote to Sanjay, right? Now whatever Sanjay votes is your vote, okay? And again, then this can be again generalized to many things. You would delegate to multiple people, then you delegate to multiple people. How will you derive your approval set, ranking, whatever? Okay, so there are such things as well.